Electrons. Okay. So which is the negatively charged one? The extra electron. And that's because there's something with more than 4 valence electrons. And the hole is just the absence of electron, which when the hole and the electron meet each other, they usually form something called an exciton, and it releases energy. It's actually helping with making electricity flow. Okay. Molecular orbital theory. Should be done. Thank you. Okay, so this slide, did you see this one? This was on my video, but I explained it really nicely for you. But it didn't save. So I'll just want to quickly show you what this means. We learned about the molecular orbital theory along with the atomic orbital theory. The atomic orbital theory, we did the whole hybridization talk. Molecular orbital theory, what were the kind of terms that went along with that? What was, So yeah, bonding orbitals, anti-bonding orbitals, sigma, which was representing a single bond, and pi, which was representing a multiple bond, meaning double or triple bond. And it also talked about like why some diatomics would exist because their bond order was stable, why some diatomics wouldn't exist because their bond order wasn't stable. So that actually is a more realistic picture of a molecule. And so as a molecule, you consider the molecular orbital theory in terms of how is a molecule conductive. Are molecules conductive?
Yes.
Some. Okay, so we normally think of molecules as like covalently bound things. Do we normally think of covalently bound things as conductors? No. Normally we don't. Okay, so this does not fit our mold, but now we're learning more, and there's always exceptions to the rules. And so the way that a molecule can be conductive is that the difference in their antibond or bonding orbital and their antibonding orbital, there's usually a big difference between that. But if the difference is small, meaning the gap is small, these electrons from the bonding orbital can jump to the antibonding orbital, and they can fall back down. And so if they can continually do that, they can conduct electricity. So with zero gap or very, very small gap, we call that a conductor because there's basically no gap between the bonding and antibonding, aka valence and conduction band. Small differences and large differences. Small differences is called a semiconductor, and that's what I did research on this summer, using conductive polymers that were able to transmit a electrical current that are generally big, humongous polymers made of carbon, hydrogen, and nitrogen. And then if you have an enormous gap, that's going to be generally an insulator, so not able to conduct electricity. And in college, you'll learn this stuff. Highest occupied molecular orbital, lowest unoccupied molecular orbital. And if you can allow for the electrons to move between those two orbital types, then it is capable of conducting electricity. Moving on. Some general concepts to know. I'm not so sure they will ask you this level of detail on the AP exam, but we need to talk about it because it is a 21st century thing. You know, did we see the Super Bowl commercial with the organic LED?
No.
Anybody?
Didn't watch the Super Bowl.
Oh my gosh, thank you. Organic LED TV that you can wrap around, I could take a TV screen and wrap around around my cup. It's like a flexible screen. They can well, they're moving to this, but they can take advertisements and wrap them around a building if they wanted to. It'd be like a scrolling screen. You take a phone, unfold it, okay, fold it back, fold it up, put it in your pocket. It's just flexible electronics. You just wait. Samsung's already making it. Organic LEDs are flexible organic electronics, or just really, really thin films that are flexible. So you just wait. Give it 5 years, you will have one of these. Okay.
Well, they said that about my jetpack. Where is that?
Those are they're being.
They do exist. You just are not rich enough.
Okay, back with me, guys. I need to finish reviewing this real quickly. Amorphous and any other solids I need to talk about here? Should have gotten this one pretty easy. Amorphous means not a structure. Okay, not a specific structure. Did that. IMFs. I was explaining this and I did not erase my writing. You know, this is a chemical change because the structure changes. These two are physical changes because the structure does not change. The stronger or the bigger change is going to be one that overcomes all of the IMFs or most of the IMFs. You can see that number 2 still has some interaction, so that's going to be probably converting from solid to liquid phase. And then when you undergo a large amount of IMF change, that's going to be a significant change in phase, so that's going to be more gaseous than liquid. Does that make sense? Shake your heads. Thank you. Okay. And this was our kinetic energy talk where you had your Maxwell-Boseman curve. And so do you remember that the lower the energy, the slower the molecules, the lesser the range of speed, and the hotter the molecules, the higher the range in speed? Do you remember this difference in graph? So the highest one, the blue one here, is going to be the hotter one, simply because its range is much wider. And so its average kinetic energy or its average speed is 650 or 700 versus one over here that's like 250. There's some gas molecule stuff. This is why we blow on soup, to blow away the hot, speedy ones, because they're vaporizing and they're also the warmest. That would, scar your tongue. So you blow them away because they're moving faster, so they can actually, evaporate out of the soup. And you can do that. And cool things down. Okay, vapor pressure. And you sketch this. You understand this. What's happening at the plateaus? Go for it, huh? Phase change. What's happening? Like, you can give me a deep. Okay, so what IMFs, if I were talking about water, are being overcome? Stronger, actually. A specific type of dipole? Hydrogen bonding, right. So our IMFs are being overcome here. Energy is being added to overcome those differences. The energy is still being added, it's just the energy is not being reflected in the temperature change because the kinetic energy is not increasing. If the kinetic energy were increasing, we would see a significant slope change. And you guys wrote down some of that. Did the math part here make sense? You actually had a FRQ question like this in your midterm. Remember you had like a melting, you do heat, like Q equals MCAT, and then heat of fusion for melting. So you actually did something like this. Okay. And there were pictures. These pictures. Do you remember phase diagrams?
Yes.
Okay, we have an FRQ with that. I'll go over that one in a second. And this is just, I explained this so well for you. Okay. This is just saying, like, if something has a high amount of external pressure, atmospheric pressure around it, it cannot vaporize unless its vapor pressure is higher than the external pressure. So it's like a battle. So boiling is just whenever the vapor pressure is overcoming the external pressure, so it boils. And if it can't, then it's going to remain in this liquid phase. So it's a fight between the pressures. Okay, this is just cool stuff afterwards.
In the video, one of the Albertans couldn't see the color. I'm assuming it was one of them.
Yeah.
I couldn't tell which one it was.
Oh, I remember that. Yeah, I watched them.
They were like, why are they're all the same color? And you were like, oh wait, you can't see that color.
Colorblind. This is this color. I had to point at them. Okay. So I'll go over some of these FRQs first. Okay. Let's FRQs, then we're going to jump to turbine. The first one is 1985, and then we're going to do 1995. Start with those two. Some of these are really just dealing with the molecules, molecular solids, and atomic solids that you guys went over in the first video. Actually, have video with it. Okay, so quickly tell me the order of the substances in terms of from the highest to the lowest melting point and why. Who's the highest? Silicon, same with that. Carbide, okay. Silicon carbide is far greater than, can you give me some more? Thank you, lithium fluoride, and then cesium iodide. Keep going. Propane. And hydrogen gas. Okay, why? What kind of bonding or IMF or interparticle force is this? Okay, so network covalence are, give me two more examples of network covalence. Okay, why is graphite conductive and diamond is not? Okay, I know it's got a sheet, but Tom, there's actually a different reason why it's conductive.
sp2, it has the ability to switch to the p orbital, so it has more electrons.
So hold on, it's got sp2 hybridization. That's right. So what's not in that sp2 hybridization? A third p orbital. So you've got these sheets. The sheets do not interact, or do they? Or can they? They what? The sheets don't have holes, or they don't have holes. They don't have anything touching except for these empty p orbitals. So if you got these, so you got these sheets with these p orbitals in between that are not occupied, but they can be occupied because they're just locations where electrons can exist. Chelsea, you with me? Okay. Distracted. So this right here is going to allow for the electrons to jump up or jump down, and that's electron flow. That's it. Why is diamond not conductive? So it has static locations where the electrons are existing. There's no mobility. Okay. So network covalence, anything with silicon is usually network covalence. It's going to have a really large amount of covalent bonds, and that's going to have to be overcome entirely, which is summative, much, much, much greater than anything else. Why is lithium fluoride greater in melting point than cesium iodide? Okay, so if charge product is the same, 1 plus 1 minus 1 plus 1 minus, you must go to distance because of, what's the formula? Okay, so the distance is greater between cesium iodide, so they're less closely bound. So the force of attraction is lesser. This force of attraction is greater, meaning its lattice energy is greater. So if you're talking ionic, you should mention its lattice energy as well, or you can just talk about distance versus this one. So this one's a small distance, this one's a large distance. Next, we have now molecular things that's not undergoing ionic, but these molecular items are undergoing different types of IMFs. So you're approaching IMFs now. Which one here? Hydrogen bonding is a stronger IMF than London dispersion on both of these, but tell me a reasoning why, and this is going into B now, tell me why propane has a higher London dispersion force than hydrogen gas. Okay, so you can say both, but if you say higher molar mass, do say higher molar mass, which correlates to higher number of electrons, because you must be talking about what phenomena that's causing this higher LDF. But what's the term that talks about the ability to form a temporary dipole? The molecule itself is blank. Starts with P. Polarizable, right? It's not polar, because if it were polar, we'd be doing DD or HB. But it's polarizable because it has the ability to form temporary dipoles. So when you're mentioning this, mention something, and this is going to feed into xenon in just a second. Higher boiling point or melting point because it's more polarizable, because it has a higher volume of its electron cloud. These are the two parts actually I want you guys to write down if you didn't already. Okay, so polarizable. And these are for my viewers at home. Mention ability to form instantaneous dipoles due to increased molar mass, which is a correlation with increased electron count number, and that usually means that you have the increased ability to distort the electron cloud. And the only thing that you could also say is that larger atoms have larger electron clouds that are distortable, or that you can distort, which would create those instantaneous dipoles. Not instantaneous, temporary dipoles. So that's just a nice way to be able to explain polarizability with some of those keywords that you want to be able to mention in your FRQs. And hydrogen gas has lesser molar mass, lesser electrons, less polarizable, lesser London dispersion forces. Okay, 1995, I think part A, basically same answer as this part right here, on 1985. What about copper to copper blank chloride? They didn't put a number. What's the difference there, Josh? You're talking about why solid copper is an excellent conductor, but solid copper blank chloride is not. Neither of them say is. They both say solid. Nathaniel.
Xenon has a higher molar mass than neon.
I'm on part B.
Oh.
Straw. Hold on, stop there. Saying metallic does not explain why it's a conductor. Give me more. Jack.
I don't see it. You look around, so like, no.
Okay. Okay, so C at delocalized electrons means they are static or mobile?
Mobile.
Mobile. Okay, you don't just say it's metallic. Most people can assume, like a fifth grader can tell me copper is metallic. You need to go further. So copper is undergoing metallic bonding, which is caused by C at delocalized electrons attracted to the core, which is the cation. You can go further there, or just say delocalized electrons are mobile. Mobile electrons can allow electricity to flow. But you must contrast that to copper, solid copper chloride. Nick, contrast it.
The electrons in solid are free to move.
Okay, so you can say they're not free to move around due to ionic bonding, or you can say they're not free to move around because they're static due to localized charge. Localized means static, delocalized means mobile. Good terms to use. Okay, so sound smart. You are smart. Don't go with the easy answer. Go a little bit further. Part C, silicon dioxide melts at a very high temperature, while carbon dioxide is gas. Blah blah blah. Same chemical family. Most of the time, same chemical family means you have the same types of bonding. Justin, help me out there. Well, I'll help you. You get me started.
Silicon
It is a metalloid, but we just talked about this part. Let me get you started, Chitra. Okay, so silicon dioxide can can bond via network covalence. Okay, compare that and tell me why. So explain further. So you're going to say that network covalent bonding sums to overall greater strength of bond, right? So this is greater than just general covalent bonding. And covalent bonding with nonpolar molecules interact via London dispersion forces. And give me more why is London dispersion important here. How does it explain its room temperature gaseous phase? So weak IMF creates weaker attraction. Weaker attraction means you can be a gas more than likely. The solid is going to be, or the network covalent most likely will be solid at room temperature. And then last, part B, I think we all can probably tell me that nitrogen trifluoride is polar. Why and what's its shape? Kevin.
Well, the shape is trivial pyramidal. Because boron only needs 6 electrons.
Right, so nitrogen requires
all 8, whereas boron only needs 6.
okay, so you can say nitrogen trifluoride requires octet, so it takes on a lone pair. The lone pair causes trigonal pyramidal structure, which would deliver its polar characteristic. And then boron trifluoride requires 6 electrons. The octet, there is no lone pair. No lone pair means it takes on what shape? Trigonal planar, which would yield a nonpolar molecule. And that's it. Okay, so I'll do the other ones later. How about look at the pre-lab for your IMF lab? And then I'm going to tell you guys how we're going to organize it so you don't have to test all millions of these. You're going to test 2 to 3 of them, and then we're going to share the results on the board. But pre-lab requires you to write the formula. Look at the formula, draw the structural formula, molecular weight, and then talk about its hydrogen bonding ability. And that's right here. I have to give you some criteria here because I do not have one propanol or I have a mixture of butanols. They're not necessarily one butanol. They are a mixture, so there might be 1, 2, 3, or 1, 2, or 3. And I do not have pentane, but I am going to tell you the answers for pentane so that we can still consider it in our pool. 1 second, please. So I do have ethanol. Check. That's in there. I have 2 propanol. So when you draw it for 2 propanol. Butanol I do have, and we're going to put that in the fume hood whenever you get there. But it's called N-butanol because it doesn't have It's got a mixture of where the alcohol group is attached. I do have methanol, we're good there. Hexanes, I also have, they're called N-hexanes. So, yeah, it says N-hexanes right there. And those are in the staying infused as well whenever you guys do test those. And I've added acetone and acetic acid to your list. So add those. It's just the only thing we won't be able to test actually is pentane, because that's not something I have. Okay, so please start in your structures. They're right here. You don't have a lab.
I have anybody.
Okay, so they're right here. There you go. Try to do them from memory. Think about what the functional group is based on the ending of the word. It also, the structure, I mean, the formulas up here, you just have to figure out the structure. Yeah, so structural is like showing the actual connections and lone pairs if you need to, details so that we can talk about the IMFs that they're experiencing. Yeah, so I couldn't squeeze it in before. I didn't want to stress it. Things like this.
starting to see
Alrighty, look up here real fast for me, and then we'll be good here. With your lab, you're basically measuring the temperature changes as something evaporates. Think about why that's important. Like, what is the correlation there? What's the relationship between the temperature change as something evaporates? John? But it's evaporating. So is evaporation, think about this, is evaporation an endothermic process or an exothermic process? So tell me why. What are we going from?
Liquid to a gas.
Okay, so liquid, close together, gas, molecules are far apart. What are you doing?
Adding energy to overcome the IMFs.
Okay, so when you're adding energy to overcome the IMFs, that makes sense, right? We're using energy. So think of it like that. We're using energy to overcome IMFs. So if we're using energy, what's the temperature going to do? Say again? It should decrease. If you are using energy, it is being consumed. It is gone, nil, not there anymore. So what's going to happen to temperature? It has to go down. That is sometimes really hard to wrap your head around. But I just want you to think about it. You have to go from something that's close to something far away to overcome IMFs. Overcoming IMF means you use energy to do so. And if you use energy, you decrease in temperature. Okay, so you guys are measuring temperature initial, temperature change, temperature dip, and you have to go to the lowest possible because it will eventually go back up. But all you're going to do is dip your temperature probe into a test tube, and I have most of them set up on the very, very back lab station with all the crap for Chem Club. And then in the fume hood, there's butanol, hexanes, acetic acid, which is pure acetic acid. Please be careful. You'll just take your temperature probe, put a little filter paper on it. They've already been cut. There's a little orthodontic rubber band. You wrap it around. You dip it in there. You very, very quickly run back to your lab station, plug it up into the probe the system that you have. Some of you guys have LabQuest that you are handhelds. Some of you guys have the computers. Just get everything pulled up. And then right now, I'm going to assign one substance to each couple. So find a partner right now. Find a partner right now. Okay, go stand next to that partner so I know who you've chosen. Have your stuff ready. Okay, Clayton and Kevin, ethanol. Maggie and Gianna, propanol. Nathaniel and Zonky? Who's partner? Okay. Nathaniel and Zonky, butanol. Oh, pentane I don't have. Methanol, Jack and Shannon. Nick, hexane, and Han hexane. And then acetic acid. Josh, Chitra, and what else did I just say? Acetone. Chelsea and Diamond, and then my last group, you guys will double up. Pick your favorite one and go. Okay. Please put your goggles on. Please be careful. Go. You need to read the lab to make sure you set up your probes correctly. If not, you'll have to redo your trials. Oh, Diamond, you've got to go run down to the office. There are probes everywhere. There are two in the front. So, yeah, Clayton, you guys see those right there? You guys can use those. There's one on the side too. Chelsea, is there a probe? Is there other two probes there? There are two. Yeah, but Clayton, yeah. So, you guys should that one. side so that way it's all without any interaction for you. So make sure you get things set up before you get your probes submerged into the air. And if you're on the computer, it tells you what specifically what files to pull up. If you're in the logger pro, the logger quest, lab quest or pro, you just have to make sure you regular initial and regular time. So I think it's very simple.